Record. All right. So, yesterday we finished with, where's my, my slideshow. Here we go. Try this. Sorry, hang on. Something's not working. Okay, this is where we left off. Are there questions you would like me to go over?
Yes, please.
All right.
I have a lot. 1B, 3, and 9.
That's not a lot. 1B, 3, and 9?
Yeah.
All right. Anybody else? I think I might sneeze before I do these. Excuse me. All right. We'll start with 1B. I'm recording, right? Yeah. 1B, page 75. Break down each vector into its x and y. Okay. So we've got, this is 80 degrees. Okay, so 80 degrees. So this is our y. This is our x. This is 15. Correct? I'm going to go a little slower just because I make less mistakes that way. So if we're going to go for x first, x is adjacent. So we're doing cosine here. So cos of 80 equals equals adjacent, which is x, over hypotenuse, which is 15. I'm just going to say right now that the way this is drawn, if you went for this kind of version of it, which is totally fine, then you would need to do 10 degrees. Oh, my phone is ringing. Why? Sorry, hang on. Jack, I'm in class. What's going on? Nope. Okay, bye. So if we're using 10 degrees, then the x part will be down here. It's all fine, but that angle matters because now the x is the opposite and y is adjacent. Okay, just want to mention that. So anyways, 80 cos times 15, 3.1. How many sig figs? 2. So 3.1. So x equals 3.1. What are we in meters or something? Kilometers. That's x. So far, so okay?
Yep.
And then so sine of 80 equals opposite, which is y, over hypotenuse, which is 15. 80 sine times 15, 14.8 or 15 if we're doing 2 sig figs. Why? Well, it's gross when we say 15, but that's the way the sig figs work. Obviously, it would be a little bit less than the hypotenuse, but with sig figs, we got this.
Could you do the X one again? Because I got a very different answer. Like I got 2.6.
80 cos.
Yeah, I think you did 18 instead of 15 by
Yeah,
accident.
Thought I saw it.
Oh yeah. Thank you. I was even going slow, but I hit the wrong button. 2.6 kilometers. Thank you. Anybody else? Questions about this one? Is that better, Kate?
Yeah.
What, you know what you did? Were you doing it this way? Maybe like this
Yeah.
style? Yeah, that's easy. Easy mistake to make. All right, number 3. football player runs 11 meters north, 20 degrees east, north and then east. So 20 meters. No, this is 20 degrees. Well, that is really terrible drawing. Then changes direction and runs 9 meters east. It's just straight east, which is nice.
Like
What's it?
it's 11 meters north to the, like 20 degrees to the east. You have 20 there.
Oh my goodness, you guys. I need a handler. 11 meters north, 20 degrees east, 9 meters east. What is his total displacement? Okay. So we need to solve for whatever this X value is. And we're going to add it to this X value. And then this Y value is by itself because Y over here is 0. Make sense? And I'm saying X and Y because that's the plane on a coordinate plane. So for our X over here, that's opposite. So sine of 20, opposite is X over hypotenuse is 11. 20 sine times 11, 3.762. X equals 3.762. The Y part of it, cos of 20 equals Y over 11. 20 cos times 11, 10.34. Y equals 10.34. Our total X is 9 plus 3.762, which equals 12.762. And then the total Y is just this. There's nothing else to add. Any problems so far? Everybody's good?
No.
Okay.
I think I was just overthinking it when I did it.
Oh, okay. Do you want me to keep going?
Yeah.
Okay. So we go 10.34 up, 12.762 over. So we can do a squared plus b squared equals c squared here. So 10.34 squared is 106.92 plus 12.762 squared, 162.87. So that equals 269.79. C, the root of this, is 16. We want 2 sig figs probably. What number are we doing? Number 3. Yeah, 2 sig figs. So we have 16, this is in meters, 16 meters. Now, because it's north and east, this is the angle that we're looking for, as opposed to kind of west and south. So inverse tan of opposite over adjacent. Opposite is 12.762, 10.34. So if I do 12.762 divided by 10.34 equals that, second tan, 51 degrees. So final answer is going to be 16 meters north, 51 degrees east, northeast. Did I do that right? Man, I get my east and west mixed up terribly. Does that make sense?
Yeah.
Yes, because no one's saying no. You're okay with this, Kate?
Yeah.
You see what you did? Yeah.
Yeah.
Anybody else questions on any part of this? All right. Look on the other side of this. This is an old physics exam. Number, did that piece of paper anymore? 9, number 9, page 75. Conductor in a train traveling 4 meters per second north walks across, excuse me, the train car at 1.2 meters per second east to validate a ticket. If the car is 4 meters wide, how long does it take the conductor to reach the other side? What is his velocity relative to the ground? Okay, so first of all, the train is 4 meters per second north, 4 meters per second north. The conductor walks 1.2 meters per second east. So the conductor, 1.2 meters per second east. Car is 4 meters wide. That says con. Car is 4 meters wide. How long does it take the conductor to reach the other side? That's the easy part of the question. What is the velocity relative to the ground? Okay, if he goes 1.2 meters per second and he has to cross 4 meters, all that we're doing there, all that we're doing there is 4 divided by 1.2. It's 3.3 seconds to get across. Does that part make sense?
Yep.
Okay, so time equals 3.3 seconds. Now the other one is, what is his velocity relative to the ground? So we have 4 meters per second north, 1.2 meters per second east. So we're gonna have, this is what we're figuring out. Does that make sense? Because even though he's just walking like straight across, he's also moving. Okay. He's this for some reason. The train's doing this, he's doing this, which means him relative to the ground is doing this. That part makes sense?
Okay.
Oh, yeah?
Yeah, that makes sense.
You want me to keep going though?
Yeah.
4 squared plus 1.2 squared equals 16 plus 1.44, which equals 17.44. I can't do that root. 17.44 equals C, which equals, I feel like I need to check my 1.2 squared. Yeah, okay. 17.44, 4.2, 4.2 meters per second. And then we got to do this bad boy. Inverse tan of opposite 1.2 over 4. What is 1.2 over 4? 0.6 over 2, 3? Sorry, 0.3? Doesn't matter. 1.2 divided by 4 is 0.3, and then second tan, 16.7 or 2 sig figs would be 17 degrees. So our conductor is going 4.2 meters per second north, 17 degrees east, relative to the ground. That relative to the ground part is important because relative to the train, he's just going 1.2 meters per second east. Questions, comments, points, suggestions? Anybody else really hungry? It's just me. Are you okay with that, Kate?
Yeah.
Anybody questions on that?
I just overcomplicated it a lot,
Okay.
but I got the same answer.
You just,
I just took I multiplied the the speeds by the time it took him to walk across. So I guess it's still
okay.
the same.
So it's like you kind of broke it down and then built it back up again.
Right.
Yeah.
So like I did 4 times 1 or 3 1/3, and then 4 was for the other one. But it worked out.
Cool. Yeah, like that's the thing, you know, there's different ways. As long as you follow the rules of math, it'll work out. So cool. We're good from there. All right. Am I recording this? Yes. All right. So now let's do some notes because notes are the best. No, they aren't. Projectile motion. This is my favorite kind of stuff in physics. You don't need to copy this diagram down, but I think it's kind of good because there's so much wrapped up in this. And like, there's going to be notes that are going to say what I'm going to say right now. But each of those little arrows represent velocity and or acceleration. Because at any point along that path, you know, I'm not going to do this so I can use my little pointer here. Any point along that path, you can get information. For one, so this is like something, soccer ball, whatever, he's kicked up into the air, reaches the top part here, and then comes down, whatever. At every single point along here, and this is very important to remember, every single point along here, after the foot is released, if we're talking about a soccer ball, after there's no contact, every single point, the acceleration is 9.8 meters per second squared down. Right here, it's 9.8 down. Here, it's 9.8 down. Here, it's 9.8 down. And that's why it's slowing down, stops, speeds up, just vertically speaking. With projectile motion, it's kind of two worlds. There's the vertical world and the horizontal world. So in the vertical world, the acceleration is always 9.8 meters per second down. The velocity is always changing. So it's going slower, 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 0, faster, 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 faster. Another way of looking at it is it is always increasing its velocity down. Like this is right here will be the highest velocity going up, but then the velocity is increasing downward, increasing downward, increasing downward, increasing downward till it hits whatever. Horizontally, you don't have to be writing all this down. Like I said, this will be in the notes. Horizontally, the acceleration is 0. And this is excluding kind of air resistance and things like that. But it is consistently 0. It does not speed up or slow down. The velocity is exactly the same at every point along the way, left to right. Initial velocity is the same as final. Acceleration is 0. Time is the only thing that kind of transcends both worlds. The time it takes to go this high is also the time it takes to go halfway horizontally. Any questions before we move on to the notes? Because it's good to kind of have that in your mind before you start writing stuff down. No, we're all okay right now? Well, let's do some notes. Do you guys prefer when I just give you the whole shooting match, or do you like it kind of point at a time?
The whole thing is fine.
Okay, now we'll leave that and let you write it down. I'll snack while I wait. Can you guys hear me chewing? Because that's really gross if you can, and I don't want you to have that. Can you hear me chewing? No. Okay. Anyone still writing?
Yeah.
Yep.
Okay, let me know when you're done, please.
I'm done.
Anybody else still writing? No, we're good. Okay, so like I said, all this stuff was kind of said when I showed you that diagram. They're kind of two separate worlds, independent horizontal and vertical motions. Okay. Anyone still writing?
Yeah.
Okay. Let me know when you're done, please.
I'm done.
Thank you. Anybody else still writing? Alrighty. So this note here, object dropped from a certain height will hit the ground at the same time as an object projected horizontally from the same height. Important to note, we'll kind of deal with that with our first practice question. All right, make my screen big. You guys correct me if I'm wrong, like you can see okay when I'm using the pen, right? I don't need to use a marker. Is anybody having trouble seeing this?
It's fine.
I know you're on your screens, it's different than in the classroom. Okay, so page 78. Page 78, practice number 1. It says a hockey puck is launched horizontally from the roof of a 32-meter tall building at a velocity of 8.6 meters per second. So you've got this building. Building is apparently 32 meters high, and someone shoots this hockey puck off the roof. The initial velocity, and that's horizontal velocity, because it says it's launched horizontally. It doesn't say it's launched at an angle. It's not going up. It's not going down. So VIX, because the horizontal, equals 8.6 meters per second. The displacement that is vertical equals 32. Because part B of this question is going to ask what the range is. That's going to be dx. So the dy is 32. The question is asking, what is the hockey puck's time of flight? So how long is it in the air for? The easiest way to figure this out is if it was just dropped, and it went straight down, because that will be the exact same time as it goes this way. If this was launched at 0, launched at, what is it, 8.6, launched at 100, provided there's nothing that gets in its way. And again, we're ignoring air resistance. We will ignore air resistance almost forever. They're going to land at the exact same time. So we need to solve for time. We also know acceleration horizontally is 0, but acceleration vertically equals 9.8. Any problems with anything? So what we're going to have to do is we're going to have to look at this vertically. We're going to ignore the horizontal for part A. We're just dropping it. And so I need something to save my. We have acceleration, we have displacement. We don't care about final velocity. So our formula will be D equals VIT plus 1/2 AT squared. Now we're going to plug in what we know. The displacement's 32. The velocity going up and down, that velocity, I didn't write it down here, VI y equals 0. Because there's nothing going up or down. It's just pure horizontal. So that is 0 times time plus 0.5 times acceleration, which is 9.8 times t squared. So 32 equals half of 9.8, which is 4.9 t squared. We're going to divide both sides by 4.9. And then we are going to get the square root. Now, something that is probably worth mentioning in case you're thinking, oh, how come 9.8 is positive here? We're going in that direction. And so that's why I wanted to keep it positive. It's easiest. If it's negative, then this displacement should be negative. Does that make sense? Why? I hope so. 32 divided by 4.9 equals that. We're going to get the root of that. 2.5 repeating, so it's 2.6 seconds. That's our final answer for that. But because it's, excuse me, was there 4 5s in there? We want to use that for the next part of the question. And this is what I was talking about rounding too soon. If we use time for the next part of the question, and we're going to need it. We're going to need it for this. Don't use this version. Sometimes it won't really affect your answer. Other times it will. Any problems with A? So for part B, it says, what is the hockey puck's range? In other words, how far does it go? Well, it's going 8.6 meters per second for 2 point blah, blah, blah seconds. So all we need to do, 8.6 times 2.555. And what I often do is I just leave this number in my calculator. This is what I had for time, so I'm just going to multiply that by 8.6. So this times 8.6 is 22 meters. Now, if, just to kind of borrow from your example, Nathan, earlier about kind of making it more complicated, if you did, okay, initial velocity is 8.6, final velocity is 8.6, time is 2 point blah, 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 you can put it into an equation and solve for it, but this is just a little bit more direct. Any questions? So simultaneously from this cliff or house, whatever the heck it is, tall building, if you dropped a puck and shot a puck horizontally, they'll both hit the ground at the same time. Are we good to move on to the next question? I'm going to do number 1 on page 81. It says a superhero launches himself from the top of a building with a velocity of 7.3 meters per second at an angle of 25 degrees above the horizontal. Oh, excuse me. If the building's 17 meters high, how far will he travel horizontally before reaching the ground? What is his final velocity? Okay, this is a superhero, so that's easily confusing because I guess the hero's just jumping. They're not flying. They're just taking a leap. So there's no kind of extra propulsion in the air or anything like that. So this building, 17 meters high. Holy leaky pen. 17 meters high, 7.3 meters per second. So 7.3 at an angle of, where did it go? 25 degrees. How far will he travel horizontally, and what is the final velocity? Okay, so the biggest thing here that we need to figure out, what it appears to me, is figure out the time in the air. And the time in the air is 2 parts. We have to figure out the kind of the vertical component of this velocity. And we'll need to also figure out the horizontal component of the velocity. The horizontal component will tell us how fast he's moving horizontally, and that'll be able to tell us how far he goes. The vertical part is going to tell us how long it takes to get to the top of the path, and then how long it takes to get down from there. Projectile motion, anytime we're talking about getting to the top of the path, from that moment, you just treat it as if it was just dropped. Are you with me? Are we okay so far? There's lots of kind of little steps in here. It's interesting too, the way the questions are, they don't necessarily kind of help you out in the textbook. Sometimes a question will give you information you don't need. Other times, what could throw you here is it asks two things. It says, how far will it go horizontally? And what's his final velocity? You can't figure out his how far he goes horizontally until you figure out the time up and the time down. It almost feels like, oh, I'll just solve for horizontal. We can't do that yet. So vertically, we have kind of two bits of info here. So vertically, initial velocity, so VIY, is going to be the sine, the red here. This is sine of 25 equals y over, which is the opposite side, over 7.3. So 25 sine times 7.3. Very important to take your time. Don't rush. 3.085. Because when you rush, it's when you make silly mistakes. And I've been modeling that very well for you, if I do say so myself. So initial velocity up 3.085. Acceleration is negative 9.8. I'm using negative here because it is going in the opposite direction as the initial velocity. It is pulling this down. Every moment, this gets less and more kind of downwise. Initial velocity 3.085 up. Acceleration 9.8 down. Okay, I feel like I'm explaining too much right now. Now, vertically, to get this first part of the question, the Fy equals 0. We want to see how far it's going to go up, and we know that it's going to come to rest when it gets to the top of the path. The displacement, we don't know, but we are going to add 17 to it. I keep doing my 17s weird. It looks like some weird n. I apologize. We're going to have to, whatever we find out from here, we're going to add 17 to it. And then, of course, we need to figure out time. Questions so far? All right, so I'm going to solve for time. You know, time or displacement, you can do either one. It doesn't really matter. Preference, anyone? No? Okay. Then I'm just going to do time. So I'm going to ignore displacement for now. So VF equals VI, I'm going to run out of room, plus AT. Final velocity 0. Initial velocity 3.085. Notice I'm doing extra decimal places. I don't need sig figs right now. Plus negative 9.8 times t. Subtract this from both sides, then divide both sides by this. So it's going to be negative 3.085 divided by negative 9.8. This is going to be our time. 3.085 divided by 9.8. 0.3148. That is the amount of time it's going to take to get to the top of its path. It, the superhero person, human, if they are human. Can superheroes be human? They're usually aliens or something, aren't they? I don't know. I'm not a comic book guy. Any problems? Are we okay right now? So this is just a piece, tiny piece of the puzzle. This is the amount of time it spends going up. So now let's figure out how much higher above the building it goes. We're going to solve for displacement here. I'm going to use this formula. There's lots of formulas we can use. D equals VF plus VI over 2 times T. Final velocity 0. Initial velocity 3.085. Divided by 2 times 0.3148. Let's circle the things I need to come back to. I'm gonna block the screen for those of you writing. 3.085 times 0.3148 equals 0.97 blah, 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 divided by 2. 0.4856. 0.4856. Total height is 0.4856 plus 17, which will be 17.4856, right to the bottom corner of the page. What is the question asking? How far will they travel horizontally, and then what's final velocity? Goodness gracious, there's steps in this one, am I right? We're not even near it yet. Any questions so far? Is everything making sense? I'm trying to go slower. Is anybody still writing? Okay, so let's figure out how long this thing is in the air for. So it's going to drop from a height of 17.4856. Initial velocity equals 0. We will need final velocity at some point, so I'm going to write that down here, that we will need to figure that out because that's part of the second part of the question. Acceleration equals 9.8. I'm not doing negative because it's all going in the same direction. Time we know to be, no, we don't know. That's what we're solving for. So we're going to do time first and then final velocity second. So, where's my formulas? Oh, I'm putting sheets in the wrong place here.
Can you move the paper down?
Oh, sorry.
Thank you.
Picky. You want to actually see what I'm doing? Sorry. Thank you. Sorry about that. Okay. Solving for time first. That's what I said. So we're going to ignore VF. So D equals VIT plus 1/2 AT squared. 17.4856 equals 0 times time plus 1/2 times 9.8 times T squared. So I'm going to divide this by 4.9 and then get the square root of it. 17.4856 divided by 4.9. The root of that is going to be the time that it takes for this thing to fall. This thing, I keep saying this thing, the superhero, from 17 5 meters high. So 17.4856 divided by 4.9 equals that. Root of that is 1.889 equals 1.889 seconds, and this is the fall. So the total time is 1.889 down plus, what was it to go up? 0.3148. 2.2038. 2.2038 seconds. Now this question is not asking any time questions, is it? No. But now we have enough to answer the first part of the question. Although I want to do final velocity while we're in this world, I want to do the final vertical at VFY, dy, VIY. This is all up and down. Time is for both. Still going to need that. The final velocity I'm going to find is completely vertical right now. The horizontal velocity, whatever, did we figure that out yet? No. But when we do, that's going to be same beginning and end. Are we okay? Okay, I'm going to do final velocity, and I'm going to do it without time, just because I don't like to use numbers that I've just found if I don't have to. I'd rather lean on the others. So when I say I'm not using time, so it's going to be VF squared equals VI squared plus 2AD. Final velocity, we don't know. Final velocity squared equals, initial is 0 because it's falling from rest, plus 2 times 9.8. I'm keeping this positive because we're going down. We're not going against anything. And the displacement, that was from this other page. The total height was 17.4856. So what I'm going to do is I'm going to multiply all this and then take the square root of both sides to get that. So it's the root of 2 times 9.8 times 17.4856. So that's 342.7, blah, 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 342.717, whatever, equals 18.513 meters per second down. We will need this later, not right now, but we will need it later. This is the vertical component of our triangle. Any questions thus far? Excuse me. VFY. Okay, no questions. I'm going to keep going. So the first part of this question asked, how far will they travel horizontally? Well, we know that they are in the air for a total of 2.2 blah blah seconds. So now we just need to figure out their horizontal velocity because that doesn't change. So the horizontal velocity, do I have like a black pen? What is this? It's orange? It's probably going to look the same. So it's going to be cos, yeah, it does. Cos of 25, I'm going to write this on another piece of paper, equals x over 7.3. Okay, I'm going to rewrite that on another piece of paper. That's going to give us the velocity, the initial velocity horizontally, but the horizontal velocity doesn't change. Back to your home orange pen. All right, so horizontal, what do we know? Velocity is, where did I write it? Cos of 25 equals x over 7.3. Therefore, VFX equals 25 cos times 7.3, 6.616. As you can see, all the more reason to show your steps. You make a little mistake, because obviously it's easy to make a mistake. I'm showing you guys that it's easy to make mistakes. And so when I'm looking for understanding, obviously the correct answer is important, but I want to see that you're kind of following the right path. If you take a wrong turn somewhere, I want to see that the majority of it is right and stuff. So please show your work. Anyways, VF equals VI, these are all horizontal, equals 6.616. The displacement, the horizontal range, we don't know. That's what we're going to solve for. Time, total time was 2.2038. This also is going to, by the way, going to come into effect when we figure out the final velocity. Acceleration equals 0. We've got more than enough stuff now to figure out displacement. I'm going to use this one. D equals VF plus VI over 2 times time. Oh, wait a minute. See, this is what I was saying before. All we need to do is multiply this by the time. I'm doing it the long way. I'm going to keep doing it this way because I started doing it this way just to show you. But this, like the first example question we did, I skipped this because we didn't need to, but now I'm just in routine or whatever. Final velocity. is 6.616, 6.616 plus 6.616, because that's the initial as well, times 2, divided by 2, sorry, times 2.2038. Notice this plus this divided by 2 is going to be this. This times this is, like I was saying before, that's the short version. I could just take this times this to get our range. So that is this times 2.2038, 14.58 equals 14.58. Is this in meters? Yes. So our first answer, we have finally a first answer, is going to be, remember, we don't round up to odd, even though the textbook does that. Frustrating. 14 meters. This is the answer to part A, or whatever, the first part of the question. We've got a sheet and a half of work, and we've only got part way done. Question. Sorry.
Wouldn't you that up to 15 because it's quote like 5.8 is a lot closer?
Yeah, see, that's the frustrating part, and I feel like I almost need to make a call here because technically we ignore the 8 because we're rounding to two sig figs. So we just look at the 5, and the rule that the textbook doesn't follow, the rule is you don't round up to odd from a 5. Do you remember?
Okay. Right.
Now,
Yeah.
Having said that, we can just kind of decide right now if we want to just make it easier and clear if we always just round. Do you guys want to do that? Would that be easier?
Yeah. Like what I was thinking is if it's just like 14.50, then I'll 14. But since it's
tell you what, let's bypass that rule. So we'll always round the way you were always taught to round. Okay, does that sound good?
Okay.
Pass it on, so we won't have to worry about making those judgment calls. And that's what the textbook will say. So you'll be you won't be thrown or anything. The textbook will affirm that. So we had 15 meters. Is everybody okay? I'm glad, Nathan, you spoke up because I was starting to wonder if everybody went to sleep or something. Are we okay with this? Any questions? Next part is relatively easy. All this paper. So we need final velocity. Final velocity. So what we're doing is we're going to do VF, nope, that's wrong, Vx plus Vy. Our horizontal velocity, it's here somewhere, is 6.616. And then that is, I'll just say forward, or from the diagram, let's say it's right. Plus, and then the vertical part is 18.513, 18.513 down, which means we're doing component vectors. So we do 6.616 across, 18.513 down. So we need to solve for this and this. A squared plus B squared equals C squared. 6.616 squared plus 18.513 squared equals C squared. $43.77 plus 342.73 equals C squared. $386.5 equals C squared. So the root of that, 19.66 equals C. Round up 2 sig figs. Is this 2 sig figs? Yeah. 2 sig figs, so we need a decimal here, 20 meters per second. But we also need to find our angle. Inverse tan of opposite, which is here, 18.513 over adjacent, 6.616 equals theta, which equals 70 degrees. So our final answer, after all that work, 20 with a decimal, 2 sig figs, meters per second. That's east, 70 degrees south. Oh, the textbook says right and down. It's fine. Either way, it's fine. It's a lot of work, hey? Welcome to physics. Any questions?
So like, why the first half? Like, why did we have to find all that? Like, what was the variable we needed?
Okay, so in the beginning, some of the things that we needed from this, we needed the horizontal velocity, we needed the vertical velocity. That all came into play for our velocity part.
Right.
But we also needed time so we could find the range. And to get time,
Oh,
we need to figure out how long it takes to go up, how long it takes to come down.
okay. That makes sense.
Yeah, lots of steps. But hopefully some of you are going, yeah, this is actually kind of cool. I hope so, because it's work, my friends. And if you hate it, then it'll be kind of miserable. But it's kind of cool. The cool thing about all the crazy stuff in physics, it's absolutely real world applicability. In pre-cal, you're like, why do I need to factor? That's a harder question to ask. But this is legit physical science and math. Thank you for that question, though, Kate. Please, guys, questions are always welcome. Any other questions? Ugh. All right, then we're done. Enjoy your day. See you tomorrow.